Calculus 2, Class 2, Part 2. We're talking about, this will be more particular, Section 6.3, volumes by slicing. So this is going to be one of two 3D sections that we are covering in Calc2. 3D calculus is covered in Calculus 3, actually, also known as multivariable calculus, and vector calculus as well. There will be these two sections that are dealing with volumes. Actually, no, three, because there's going to be also one on areas. And what we are doing here is we are looking for methods and ways to find volumes of particular objects, objects that have a particular quality. And that is, they must be radially symmetric. They must have a circle when you cut them in one way. So take a look at a bottle, right? You take a look at the bottle. If you cut this bottle anywhere, this way, you will always have a circle. Now, this way, the bottle has certain function, which we can probably model with some f of x, right? But when you turn the bottle this way, and if you are to cut, you will always have circles. A lot of objects will behave that way. Take a look at the marker, which is almost a cylinder, right? So think of a cylinder, which is a straight pipe. That's probably the easiest example. But then there's the cup over there. Can you raise that real high, right? That cup. Awesome. So we have all of these different shapes. Let me draw a cup. Pipe. A bottle, which is terrible, but you all get the idea. This is really terrible. It's terrible to the point that it annoys me. Now you will call this perfect otherwise. And for all of these shapes, we are going to find the axis for rotation. And as you rotate just a half of the shape, it will create the 3D shape. So I'm going to ask you now, if I am to draw this and rotate, what do I get? A cone. So this will be a cone. Awesome. Baseball bat. Yep, a baseball bat. So a lot of shapes out there, right? You can get the football as well. Right? Rotate that, you get the football. So a lot of shapes out there can be obtained by simply figuring out some kind of function f of x that needs to be rotated around the axis. And as you rotate this in space, you create a 3D object, and that 3D object will have volume. So now what we are going to do is we are going to take a look at the formula which computes the volume. And we'll be able to know now the volume for the cone and the volume for the cylinder. You can forget all of those formulas that you had to memorize before. In addition to that, you will be able to actually compute the volume of the football, which earlier you couldn't do well. And one of the project questions is related to this concept. You can also figure out the volume of the cups that you are having and so on. So take a look at that cup, right? What's the volume of that cup? It has to be printed on it. You look around, it will say, I don't know, 16, 24 fluid ounces. It should say something on it somewhere.
On the bottom.
It's all wet.
Okay, how about that one?
16.
16?
Yeah.
So can you read that? So the company there claims that that's 16 ounces. Is it? Yeah. You take a measuring device, such as a ruler or something, take some measurements around, apply these formulas to it, and if it's not 16, if it's less, well, hey, you don't have to go to school anymore, right? You're set for life. It's New Jersey, right? US, you get the idea. You get the royalty from the company you found the flaw they had there for years. All right. So let's see how this stuff works. We hopefully all understand that every time we have any of these shapes, when you look in the side view, it's going to be a circle, 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 and so on. Now, what is the volume? It's going to be area of the base times the height. So if you think of your base, right, times the height. We're going to take a look at more at these concepts even more when we move to Calculus 3, obviously. So let me write the formula for this and then see if we can decode what's what here. So volume is going to be pi integral a to b of f of x squared dx. I'm going to box that one. I'm going to put a graph on the side. And we're going to look at this. So now, I want to ask you a quick question and see if you can actually see and decode these formulas. I'm just going to bring this a little bit closer so it doesn't miss anything I say. Imagine a cut over here, which will produce a little disk. So I'm going to draw that disk in. I cut a little disk. It's going to have a very, very tiny thickness there. Delta X. Think of a, you still know what the CDs are? Okay. So think of a CD, all right? Actually, wow, Blu-ray. There we go. All right. Yeah, DVD. All right, but that's still now that also becomes ancient. Nice. So Blu-ray, right? Soon the whole concept of teaching, when I mention CD, it will be like open your history book on page 37, look up CD, and now we get to talk about the disk method in mathematics, right? Because everything is going to be digital. People have no clue about anything. It's going to be awesome.
You still need water.
Yeah, but yes, I'm listening. You caught my attention. Yes, keep talking. So, guys, what we're going to do is we're going to take whatever your favorite cutting object is, like a chainsaw, let's say, and make a very thin disc. All right? So you have a disc. And let's think about this disc, because this disc is going to have a volume, right? It's going to have volume. It's very thin. So you're literally thinking of a CD. It's going to be area of the base. You put the CD flat down, right? And the base of it is a circle. Volume is always area of the base times the height. So what is the area of the base? Pi r squared. Do we see pi r squared? Hopefully we see pi r squared because look at your r. It stretches from the axis of rotation to the function. Do you see that that's your r? The f of x is actually your r? And we are allowing r to be f because it's changing, right? Over here, the r is smaller, and then it grows, it grows, it grows, right? So it will follow the contour of the baseball bat. It will follow the contour of the cup or a bottle or whatever it is. Radius is changing. So we are capturing the changing in r as f of x. So that's the reason why you have f of x squared. That's your r. Now some textbooks were actually going to call this function r of x. So I hope you see the base, right, for the area. Area of the base is pi r squared times dx is the height of the disk, right? If you take this disk and you put it flat on the ground, dx becomes its height. And that dx goes from a to b to capture the entire thing under adding all of the disks together. So if you want to have a stack of CDs, think of that as a stack of CDs. And that's what the integral sign does. Adds all of the CDs, like all of the little disks on top of each other, and each disk is different size, right, to accommodate the shape. So you have the integral sign, which will add all of the disks together. So individual disk, each individual disk is going to be area of the base, which is a circle, times its height. Height is infinitely thin, but we have all of the infinity of them to get the entire shape in. The formula works. It's very simple to remember in that case. If you know from your calculus 1, which you should know from your calculus 1, that the integrals, I erased it, that the integral area under the curve is f of x times dx, then you know that this is your height and a to b dx is the entire length. So if I draw a function f of x and I have from a to b, this length is a to b and dx, and the heights over here are captured by f of x. So same thing happens there. All of our radii are captured by f of x squared. That's our r squared every time, times pi. Pi r squared is the area of the bottom, times the height, which is dx. Stack all of them up from a to b, and you have your shape. We also have the one in the dy direction, which is going to be pi integral c to d f of y squared dy. And believe it or not, this lecture is done. We just need to now do examples of these. So technically now it's hard work. Do you know Calc 1? Do you know how to integrate? If you understand the formula written in this way, you should be able to set up every problem and do it. Now there's also washer method, which is an upgrade to this, more general case. So the volume for the y direction is identical except in terms of y. So next time you go for an ice cream, you can bring this stuff up, because now you know how to compute the volume for the cone, right? Which means that if all the rest of the ice cream melts into that thing, you will know exactly the volume-wise how much ice cream you have. And if you're allergic to ice cream, do it again. Do it just because you can. You're there. So let's take a look at that cone situation. I have a piece of a function right here, and I know what's a good length for the for the cone. Let's say 5 inches tall cone, and maybe 2 inches wide. So what's the volume of that cone? We are going to rotate that around the x-axis. This function will appear on the other side, and it will create opening there, and it will be a cone. So let's see. We know that we are integrating. So volume is equal to pi integral 0 to 5, because the cone is 5 inches tall. 0 to 5. The function, well, yeah, we gotta write the function. Well, it's a linear function, slope 2 over 5 x. We square that one, dx. So this is your function f of x, which is the line for the cone. And I got that line just by looking at the graph, because I know the slope, right? 2 over rise over run. So rise 2, run 5, and it has to be positive because it rises to the right. So it's positive 2/5 x. And then it goes through 0, 0, y-intercept is 0. So no plus b. Square 2/5, you get 4/25. So 4 pi over 25 integral 0 to 5 of x squared dx. Compute that. 4 pi over 25 x cubed over 3 from 0 to 5. It is awesome. 4 pi times 125 over 25 times 3. These guys cancel to 5. 20 pi over 3 inches cubed of ice cream.
Where did you get the 4 pi over 25 from?
I have to square this quantity here because it's in parentheses.
What's that last one you got after 25 over 3?
Inches cubed.
Oh, inches cubed.
Yes. So this is the first introductory example. Now let's say that the cone had a, well, let's figure out something else now. So what happens if I am machining a piece made out of metal or something that is necessary for some kind of machine, and the shape needs to look like this? So it's solid piece of metal with a hole in the middle. Clearly something that you obtain by rotating this. So what now? How does the shape looks like? Well, this is what you're rotating. You're rotating this triangle around the x-axis from A to B. And observe what you have. Outer radius, inner radius. You can call them F and G, and certain books they're called capital R and lowercase r. Now, I hope that you are going to see here a progression where in Calc1 you had a single function for area under the curve, and then in 6.2 we said between two curves, and you had top minus bottom. You have the exactly same situation here. You have the outer radius and then the inner radius, and you don't need this over here. So it's going to be outer radius squared minus the inner radius squared, and that is the more general formula known as washer method. Volume is equal to pi area A to B, f squared of x minus g squared of x, everything dx. And this is when you have what I call a holy object. All right, you have a hole inside. It's centered. Obviously, everything has to be radially symmetric. And in this case, you have the outer minus the inner. So the one that is further away from axis of rotation minus the one that is closer by x rotation. The proof for this and the derivation for this is exactly the same as the area between two curves, because you have the integral that computes the volume all the way out, integral that computes the volume inside, which is the one we don't need. When you subtract the two, you get exactly what you do need. There is also a formula for the y direction there. Which is, again, if you're using dy and rotating on the x-axis. So, in terms of theory, this is all you need to know for the disk and the washer method. We did only one example, so next class we're going to do more examples for this. And then we're going to continue with 6.4 and 6.5. And that would be on Monday, and I believe we meet in a different room. It's in a, studio 10. Let me just